Okay. Looks like there's a few more seats in here today, so that means that either lots of people dropped or lots of people are watching on video, which is fine with me. Gives us all a little bit more room if you want. I have to apologize up front. As you can probably tell from my voice, I have a terrible cold right now. I've been taking this like generic daytime like cold and flu relief. Don't do it. It's not worth it. Trust me, it's not worth it. It's I don't know what symptoms it's supposed to be trying to get rid of, but it seems to be giving me more symptoms than helping out. But I will try to make it through this presentation today. If I like fall on the floor, call 911, please. Do some CPR if necessary. And if I fall on the floor and need to call 911, then tonight's review session is probably canceled. So that's it, probably. You never know. I could rally. Who knows? So let's see. So we're here on day 2, even though it feels like we've been in class forever already. Right? Hopefully you guys have been working on homework 1. Hopefully it hasn't been too difficult. I purposely didn't make this one that difficult. If you are having trouble with it, that's fine too. I probably would suggest coming to tonight's review session just to kind of get your hands around C++ a little bit. And then there's office hours over the next couple days. Who is still having technical issues with like Eclipse or something else? A few people? Yeah, if you're still having technical issues, let me know. We'll fix them. Everybody who's come to me, we've been able to fix their issues. And some have been really wacky. Like there's a couple people who had time zone issues. Like they're from another country and their computer's set for like, not a time zone, but like a region. And that screws up like logging onto Eclipse. It's really bizarre, but we figured it out. So we will figure that out. If you do need a couple extra days on the assignment because of technical issues, let me know. OK? So I'm going to be flexible on that part of it. OK, any questions before I get going? We'll talk about a lot of things today. All right, yeah, lots of stuff to talk about today. First things first, the review session is going to be at 7:30 in Halligan 102, which is the first floor right when you walk into Halligan on the left. And it's going to be about an hour long. You can come and go as you please. If you took Comp 11, you probably will find it a little bit like slow. So bear in mind. If you do want a refresher, you're perfectly welcome to come. OK? And I will put that online too. So if you want to watch the video instead of coming to class or to the review session, you can. OK, labs start next week. Labs are only Mondays and Tuesdays, like Mondays after this class and then almost all day on Tuesdays. Hopefully you can find a time that fits. If you definitely need one particular time for lab, I suggest going on right about at 6 o'clock, right after this class ends, and signing up. If you do run into a problem where all of a sudden the whole lab is filled and you couldn't get into it and you have to, email me. We'll work something out. OK, the labs only fit like 22 people. So it's and let's see, there's 9 labs and there's 22 people in a lab and there's like 200 of you. So that actually doesn't quite work out actually. But so I think there's like 100. Maybe there's 196 of you or something right now. But on that note, if you haven't yet gotten enrolled and still need to give me an ad form, please do that like now so we can get a good count. Or not, I mean, if you can't do it right now, bring it to me or email me or whatever. But everybody should be able to get in the class. And if you haven't gotten on Piazza yet, definitely do that. If you don't know how, let me know. OK? Yes?
How do you sign up for the lab?
Yes, how do you sign up for a lab? Good question. This is the lab sign up right here. OK? Bruce runs it, so there it is. OK? So at 6 p.m. you can go to that. And unless Bruce did something wrong, it should be up and ready to go. Yes?
If you're not registered yet, will that preclude you?
Nope, this has nothing to do with registration. So go ahead and do that. OK? All right, any other questions on lab sign up? No? OK. Want me to leave it up there another second? OK. You can ask me after class. You can't get it. OK. Let's see. So we're going to do a few other things today. I'll do a little what I like to call a Unix tip of the day. I know Unix. You guys did like the terminal for Comp 11 if you were in Comp 11. If you weren't in Comp 11, Unix might be like this weird brand new thing to you. And what I'll do is a few kind of tips where how to do stuff. The first one's like easy, and you probably already know this stuff anyway. And then I'll do a little Eclipse tip of the day as well. And I'll try to intersperse those throughout the lectures as we go through the semester. Then we will talk about interfaces. Now, if you took Comp 11, I believe you talked a fair amount about interfaces. So we'll kind of go through that pretty quickly. And you're nodding your head like, oh, I know it all about interfaces. Yeah, OK. We'll go through that pretty quickly. And then we will talk about abstract data types, which, yes, you talked about that? Or yeah? Oh, you did? Oh, all right. Well, we'll go through that quickly, too, then. And then we'll actually get into the meat of like what data structures are and what the differences are. Then we'll talk a little bit more about homework 1. And if you've already done it and submitted it, just sit back and relax and be happy that you've done that. We'll go over that a little bit more. Then we will talk a little bit in detail about dynamic arrays, which, again, I know this is all review, but it's always good to kind of get a little bit of review out of the way early. And then we will go into a little more detail on memory management. Did you guys use Valgrind at all in Comp 11? A couple people did. Not too much. OK, that's good. Valgrind allows you to find out where the memory leaks are in your program. So in other words, if you ask for memory from the system and then you don't give it back, Valgrind will say, hey, you didn't give that memory back. So it tells you where that is. And we test you for that when you provide. So if you don't give back all the memory, you lose points. OK? So we'll talk about that. And then we'll do a little bit on testing your code as well. So hopefully you got a Piazza email from me at some point in the last few days about testing and about some of the ways you can test your own code. We'll talk a little bit more, and I'll answer any questions about that. OK? Any questions before I get going into the Unix tip of the day? Awesome. OK. So a couple quick ones here. You guys already know some of these, I'm sure. ls tells you what files and folders are in your directory. But it's not just like ls. Most people just type ls, right? But there's lots and lots of different flags you can use for that. I'll show you that in a second. And then cat is a file that stands for concatenate, or a program stands for concatenate. And it actually allows you to print out a file. So if you just want to take a quick look at some file, you use cat on it, and it boop, prints it right to the screen. And you don't need to worry about opening up an editor or whatever. A better way to do it, though, is to use a program called less, or another program called more. They do really the same thing. More came before less. I don't know why they named them differently, but whatever. They do more or less, no pun intended, the same thing. And so that prints out the file, but it's like one page at a time, so you can seal it. So anyway, let me show you that. All right. If we log on, and I just do ls, obviously, it lists all the files in my directory. Right? Those are all the files in the little folder I have. And if you do ls-al, those are two flags, a meaning all, and l meaning like a list in a certain format. You'll get this funny looking list of all the files to include the hidden ones. Anyone know what the hidden files look like in Unix? Yeah. They start with a period, yeah. So like .pulse, right here, I should use the long pointer here. There we go. .pulse, wherever it went, there it is, or .pulse cookie or whatever, those are all hidden. So if you do just a regular ls, they don't show up. So if you want to find where some folders are, and you know they exist, if they happen to start with a period, you won't see them with a regular ls. A really important one that may come into play sometime later is this .snapshot folder. That's like super important because that's a backup of all your stuff. So if you ever delete your stuff, it generally has a backup within the last 4 hours of your stuff, and then 4 hours before that, and 4 hours before that, and then like a day before that, and a day before that. So it's got lots of backups in there. And it happens all automatically, and you don't have to do a thing. So it's really nice when you accidentally delete a bunch of files. OK? So that's ls-al. There's a command called man, which stands for manual. If you do a manual of ls, you will see that there's all these flags. It's hard to see on this screen, but there's all sorts of flags here, probably like 100 different flags. So you can do lots of different ways of getting your directory listing if you want. OK? So I mentioned the cat program. If we do cat, and then one of the files is trie.cpp, trie.cpp, it will actually print the whole thing to the screen. And it went by really fast. So there's the whole program, right? But if you want to see it one page at a time, just type less and then trie.cpp. And that will actually print out just enough. And you can use the arrow keys to go up and down and just kind of walk through it. And it's a good way to just get a feel for what's in your program. If you want to look at the header file or something, it's easy to do it with less to see the file. And then you just type Q, and it brings you right back to where you were before. Yes?
What are the limitations when typing file?
You generally have to do text files. Yeah, if you try to do a binary file, it'll give you all sorts of weird characters and so forth. Yeah. OK, any questions on those? Just a quick little one. I'll give you more interesting Unix tips of the day later. OK, and then Eclipse. Anybody get a message on Eclipse that says workspace in use or cannot be created? Anybody seen that one? Did you figure out how to get past it from Piazza Post? I put some stuff on Piazza. If you get this, what this generally means is you've been working on Eclipse, and then either your internet goes down or something else crashes or something, and the homework server still thinks that you've got an Eclipse running, and it won't let you use your workspace. Well, I wrote a little script that you can type in that's just this, /comp15 public HTML files kill eclipse.sh. And it says, hey, Eclipse, you're dead. And then just whoop, and then you can pull it up again, and it should work like that. OK? Anybody give up on Eclipse because they're just too slow or too? Yeah, a couple people, I know. Sorry. Just a suggestion to use it. In the lab, you might want to pick it up in the lab. Lab's much quicker if you want to use it in the lab. OK. Other questions on that? Any other Eclipse questions at this point? I'm trying to get the TAs to understand Eclipse a little bit better. They tend to not. Yes?
I couldn't get it to build the file.
Couldn't get it to build? Try, did you open a project? You created a project like we talked about? And then click on the actual project name and then try it? That might work. If it doesn't, see me. It's not a hard thing to fix. Cool. OK, yes?
I was trying to go line by line and accidentally jumped over instead of jumping in or whatever you're supposed to do.
Oh, yeah.
Is there a way to go back, or did I mean, I just restarted it and went through?
Is there a way, yeah, if you're doing the debugger and going through, there's not really a way to go back, but you can do the step out function, and it will generally take you back to the next line where you probably meant to go. So try that one next time. But you can't go back. You can go forward, though, still in an easy way. I can show you that, too, if you come to office hours sometime. All right. Anything else? OK. All right. So programming interfaces. So you've seen a lot of this in Comp 11 if you took Comp 11. But an interface in programming is just the contract between the person who says, hey, I want this to be what my program does, or at least my class does or something, and the programmer who writes the actual functions. OK? Usually, we put this interface into the header file, the .h file, and we say, here's all the functions that you're responsible as the programmer for creating. And this is what they do. A lot of times, we'll put comments to say, hey, this should return this in the following format, or this should take a certain parameter, or what have you. And we normally put that in the comments. But that's the interface, right? That's like saying, hey, here's our contract between what you're going to create and what I want you to create. OK? It's fairly straightforward. But that's what we call the interface. OK? Here's an example from homework 1, the card.h file. Now, you guys weren't responsible for that. You aren't responsible for that. But here's what it looks like. It's just the header file, basically. And it says, look, card has all these functions. It's got a constructor. It's got two constructors, actually. It's got a destructor. It's got a print card, all these other functions. And you are responsible for doing those. And you have to, if you are going to, for instance, set the suit, right, you're going to have to provide it, or whoever runs your code is going to provide it a suit, which we've defined elsewhere, actually. And that's the whole function right there, actually. So this is actually a little like the function in the header file. We don't normally do that, but for small ones, we allow it. And that's it. And so that's your interface for this card function. OK? For same card, for instance, that's one of the functions you have to write uses same card. Right? What does same card do? Well, you can look in the interface, and you can say, OK, look, it returns true if the cards are the same. So you're in a card class. You get passed in another card, and you say, hey, is the card that got passed in the same as my card? If it is, return true. Otherwise, return false. And look, it's a pretty easy one-liner, actually. It says return rank, right, which is the 2, 3, 4, 5 all the way up to ace, equals if rank equals the card's rank, in other words, if my rank equals the card's rank, and my suit equals the card's suit, return that. And that's going to be true if those two statements are true, etc. Okay, so that's like, this is like the interface, and this is the what's happening in the interface, the actual function. Not hard. Okay. Here's another one. Let's see. Deal card from bottom. You didn't have to write this one either, but this deals a card from the bottom of the hand. Now, if you're creating the internals of this, right? What defines the bottom of the hand? The beginning or the end? You kind of have to know that from the interface, right? So I mean, we say here, look, the bottom of the hand means the first card. Like, that's kind of important. Now, in reality, as long as the back end is doing things correctly, it actually doesn't matter. As long as it works out all right that that in the background you know which end is what we call the bottom of the deck, then, or the hand, then that's fine. But in other words, you need to know a little bit about it to make it precise. Okay, so deal card from bottom of the hand. The bottom is the beginning of the hand. That's just a little comment saying, hey, this is what we're talking about. We're removing from the head. You have to write this one. And then we're adding the card to the top of the hand. So we're removing a card from like the deck and putting it into a hand. That's what this is doing, right? Interface versus the actual function. Okay. Another example. This is one of the ones that we give you that you guys do. So I guess I'm doing some of your homework for you. Has card, right? If an array has a card, how do you know? You actually have to do a loop. You loop through all the cards. If you get one card that's the same, you say, yep, it exists, so you return true. If you get all the way through the loop and there's no card there, then you return false. Okay? Interface, function. Straightforward. Okay? Hopefully mostly review. Okay? All right, so that's an interface. Now, what is a data structure? Well, Wikipedia says, look, a data structure is a particular way of organizing data so that we can use it efficiently. This is all about what I talked about on day one. I'm going to keep hammering away at this efficiency thing all semester. Okay, by the end of the semester, you're going to be sick of hearing me say, is it efficient? Right? That's what a data structure is. We organize the data so that we can do whatever we're trying to do efficiently. Okay? The functions for that data structure fulfill the interface requirements. Now, we're going to talk about another word that's very similar to, like, it means almost the same thing as this in a minute. But the functions fulfill the interface, and those functions comprise the data structure. It doesn't matter in the big picture what's behind that interface. Okay, so the fact is we can use the array data structure, because an array is an organization of data. We can use that array data structure to meet the requirements of the interface, or we could use some other function or some other data structure. In other words, we could use, for instance, a linked list, which is what you are going to be doing for homework on next assignment, right? You're going to have the exact same interface, same functions. Now you're going to have to write them in linked list form. Okay? And as I said, we learn about linked lists, and then I tell you never to use them again. Don't do that. Yeah, yay. They're not that fun. There's lots of like tricky parts to linked lists. If you don't remember that from doing them in Comp 11, you will get all of that again to try to make sure you don't have those corner cases that trip you up. In fact, in the linked list lecture, which is like next week, at the end I put anybody know who created C++? Guy's name? What's his name? Bjarne Stroustrup. Where's he from? Do you know? It's a Scandinavian country, but I forget which one, I believe. Anyway, he created this, and then he has a little video on YouTube that you can look up that says, it's like 7 minutes long, and it's like never use linked lists. And this is the guy that created the language, so you should probably listen to him. Okay. All right. So we can use different data structures to fulfill that interface. Okay. So there's kind of the difference there. Now, the other term that we're going to have to know is this thing called an abstract data type. An abstract data type basically is the interface. Like, you can kind of think of it that way, but it's the way we define our data structure. Okay. So really, it's more or less the interface, right? But the abstract data type is telling you, hey, this is what you need to do. I don't care how you do it. right? Now, in real life, you do care because you don't want it to be super slow, so you don't want to use linked lists. But in the big picture, as long as it meets the interface requirements, then you can be fine. You're fine as far as the interface is concerned. If your function returns what it's supposed to when you ask for it, then whatever happens in the back, you could like send it off to monkeys via email or something, and it can return, right? Then that's fine. It's still part of the. You still have a appropriately written interface. That would be really slow. Okay. All right. So that's the difference between an abstract data type and a data structure. From homework 1, our abstract data type is this list. Right now, you're creating functions in this class called list dynamic array. Right? That's your class. Next week, it's going to be list linked list class. But it's all the same functions, right? Because the data structure part is the list, and you're creating, or sorry, the abstract data type is the list, and you're creating the data structure from that. Okay? It doesn't matter that insert@head in one case uses a linked list in the background, or the other case uses an array. Doesn't matter, except that one might be slower or faster. That's really the big thing. Okay? That's going to be the difference between 1 and 2. Questions on that? Differences between abstract data types and linked lists? Or abstract data types and data structures? OK. All right, let's go back to assignments 1 and 2 again. If you've already done this, again, be smug that you've already completed all this, right? We've created the classes card and the class hand, right? Cards are, somebody asked on Piazza, hey, I want to make sure I've got the order right. That's great. If you're writing a program that's going to use these, that's fine. You don't actually have to care about this. For your data structure, it doesn't matter because the card class is already written for you. So you don't really, for the homework assignment, you don't actually care what these suits and all that is. You don't really have to worry about it, OK? Because I wrote those for you. The hand is another one. You actually don't need to worry about that either. In homework 1, hand has a private data member called hand, which is a list dynamic array. Guess what it's going to be for the next assignment? The linked list, right? But it's the exact, everything else about hand is the same, except that the individual data structure is going to be different. And that's going to kind of show you how you can do the same thing with 2 different types of data structures. OK? All right. OK, what can you do with hands? Well, you can deal a card from one hand to the other. Right? You can add cards to hands at the beginning and in a particular position. You can remove cards from hands. You can shuffle a hand. You can order a hand based on suitor rank. You can check if a hand has a card. You've written that. We already wrote that function, actually. And you can print out a hand. All of these are part of the interface for a hand. Now, this isn't everything a hand, if you're playing cards, can do. So you could actually add more things to this. And if you want to go above and beyond for this project, you might want to do something like that. We'll talk about some examples of that in a little bit. OK, so let's see. These are all the functions. We mentioned these the other day. These are the ones you have to write. We are going to go over in much bigger detail the expand function in a few minutes, because that's kind of important when you get to dynamic arrays. OK, you actually don't have to do any expand function for linked lists. If you remember your linked list, you'll realize why relatively quickly. But we'll talk about expand in a little bit. But the other ones you have to write for both homework 1 and homework 2. Okay? And by the way, for homework 1, we give you lots of comments. For homework 2, I'm not going to give you any comments. Or functions, really. You're going to have to do the functions on your own. But just one step harder, I guess. All right. Let's see. You have to meet the criteria in the interface. OK, that's kind of the whole point. Right? We want it to do what the interface says. If you're going to do something above and beyond, you can certainly add things to the interface, but don't make it so that it breaks the ones we ask you to do. That's all I ask. Okay? We've got comments, tests. We'll talk about tests in a little bit. We'll talk about tests actually at the end of the lecture. We will run some tests during provide. If you've already used provide for this class, you'll see that it prints out whether you passed a test, and if you failed the test, it prints out the code that we tested it on. Right? So it says here, look, your program failed this test with this code, which is good because that means you can take that code, copy it, put it into your program, and debug it that way, right? So I purposely did that so that you get a little feel for, oh, this is what a good test looks like for this kind of code. Okay? We can run other tests. We reserve the right to run other tests on the code as well. You should be writing some of your own tests as well. Okay? And then the other day, I spent some time talking about formatting your code properly. Has anybody ever heard of the obfuscated C contest? OK, have you heard of it? So when you write programs, right, we want them to be human readable. Right? That's kind of one of the biggest points. Right? A C++ program is made for humans. Right? The compiler translates it into machine code so that the machine can read it. But the C++ part is for you to get, to understand. There is a contest. Let me see if I can find it on here. Obfuscated C contest. Here we go. All right. And the obfuscated C contest, let's see. Do we have the source code? Here we go. Obfuscated obviously means that it's hard to understand. You don't know what hard to understand means until you see some of this code. All right, let me show you what I'm talking about. I'll show you on one of the next lectures, a couple lectures, I'll show you some obfuscated code, and it's relatively crazy. This one's a good one. This is hard to see. There we go. OK, see this? Like, you see a little like I written up there in big letters? Like, that's real code. Like, that's actually like legitimate C code right there. And it does something. Right? This whole program actually does something. And this is what we mean by when we say obfuscated. Right? You can see like return A, and you can see real C, like C or C++ stuff in here, right? But like a curly brace, whatever. But it's like super duper hard to understand. Don't make your code like this, please. OK? If you want to go above and beyond and like submit one that looks like this, we'll probably read it and laugh. But it's definitely crazy and hard to understand. And the only person who really probably understands this straight out of the box is the guy who wrote it. And it takes a very special person to write this sort of stuff. You know what I mean? I don't know what all this is about. Kiss, 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 kiss. I don't know. Who knows? But anyway, I'll show you some running obfuscated C programs next week. And I think you'll get a kick out of them. But don't make your code look like this. OK. All right. So as I said last week, if you do breeze through this assignment, awesome. Right? That means you're right up to speed. You're ready to go. And that's terrific. If you do and you feel like, hey, that was too easy, and what am I doing taking this class when it's so easy? Trust me, things will get harder, number one. But number two, you can always do some above and beyond. For instance, anybody play poker in here? Not in Vegas, I hope. Most of you. Some of you are probably old enough. Anybody play poker in Vegas? A couple people? Yeah. Did you lie about your age, or are you really like able to? You're not answering. I see. So if you play poker, there's a hand called a flush, right, which is all of the same suit, right? Well, if you wanted to, you could relatively easily, I think, create a function that just says, look through the hand and tell me if it's a flush. Easy enough, right? But there's other ones too. There's straights, and there's straight flushes, and there's 2 of a kind, and 3 of a kind, and full houses, and all this kind of stuff. If you were writing a poker game, you might want to add to the hand class and say, hey, is it a flush? Is it a 2 of a kind? Is it a 3 of a kind? Et cetera. Or even better, you could write a function that says, what hand is this? Right? Or even better, if you have 2 hands, what do we want to know?
Which hand is higher?
Yeah, which person's going to lose money, right? You want to know which hand is higher, right? So if you want to do something like that, by all means, go ahead and do that. Put your information about that into the README file and say, hey, I created this little poker game, and then I took all sorts of money from my friends by playing it with them or whatever. Then that's great. And we'll take a look at it. But if you don't put in the README, we won't necessarily know to look at it. OK? We won't actually look at your main file at all. Like, we use our own mains for the tests. So if you want to have the main do other fancy stuff, then that's fine. OK? All right. Questions about that? If you're having trouble, there are still office hours this week. If you're really having trouble, I will probably be lenient about giving you a couple extra days to do it. Yes?
Do we need to add comments to the files that we're not editing?
No, you don't need to add any comments to the files you're not editing. And in fact, the files that we've already given you, we've done most of the comments already. Just try to mingle them together. Like, don't have like comment, 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 code, 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 code. Put like comment line, comment line, code line, if it tells you what to do. Like, for instance, in the expand, right, it says create new array. Right? Well, and then the next line should be your code creating the new array. And then it says, it says copy the array to the old one to the new one. Then the next couple lines should be copying the code to the new one. That make sense?
Okay, but that's only if it's not self-explanatory.
Right. If it's not self-explanatory, read the commenting guidelines if you want to know what more details. But for this one, we've written a lot of comments. You should intersperse those. So, okay, good. Any other questions on that? No. Okay. All right. Yes?
Are we supposed to understand all of your code?
No, that's a good question. So, well, yes and no. I mean, you should understand the C part of it. But so, for instance, there's a copy constructor in there, and an operator equals overload. I mean, you've probably never seen anything that said like it said operator equals and then parentheses da 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 da. Right? I wrote that for you. What this is all about is if you want to say, if you have two dynamic arrays and you want to say dynamic array A equals dynamic array B, unless you write this, this won't necessarily do what you think it's going to do. So we will talk about that over the next few weeks. You do not need to understand that now. But we'll talk about that over the next few weeks. But yeah, good question. There's a couple things in there I put in there and didn't expect you to necessarily get quite yet. Okay? But we will go into details about that a little later. Yes?
I had a question about it can get bigger, but when we're removing a card, it doesn't specifically say to make it smaller, so this doesn't
Right.
go forever.
Yeah, right. Our model basically increases the dynamic array as big as it needs to be, and then if we remove all the cards, it's still got that much memory.
Okay, I
Yeah.
just want to make sure.
Yeah. You don't need to worry about shrinking it. You could, I mean, if you wanted to, you could say, oh, I've wrote another function to shrink it. And if you want to, you can do that. But generally, we won't worry about that too much. OK. All right. So array. Anybody else? OK, arrays. So arrays are, as I said the other day, kind of the basic part of a computer system memory. Right? Everything is in array form, right? By the way, do you know when you erase, you're supposed to erase up and down and not side to side? You know why? Exactly. Who said that? You must be a teacher. Must know that. Yeah. If you do side to side, your butt jiggles back and forth, right? OK. So arrays. So sorry, I'm a bit punchy with all the drugs. OK. So when we create an array, right? We already know about arrays and the fact that they're indexed and so forth. The computer only knows that. Everything else has to fit kind of into that model in some form or another, right? But basically, this is an address in memory. The next part of the array is the next address in memory, we call it. And then the next address, and they're individually addressable in that you can say, give me index 3, what that value is. Give it to me. Give me index 1. Give me whatever. You can do it in random access, which is kind of nice. And it's very fast because it's very low level. OK, so arrays are very good for that from that standpoint. When we talk about arrays, this also should not be news to anybody. When we talk, well, unless you haven't done pointers before. When we talk about arrays, we can access the elements in a couple different ways, right? We can say x bracket 3, which gives us actually the fourth element because elements are 0 based. Or we can do the exact same thing, and we can say asterisk, which means dereference, which means, hey, give me the information at this memory address. And x happens to be a pointer, which points to some memory. And it says, give me the information at where x points plus 3, which is the exact same thing as saying x bracket 3. OK? So let's look at this code for a second. In this case, we say int capacity equals 10. And then we say int star or asterisk x equals new int capacity in brackets, right? This tells the memory system. We'll go into this in a little bit more detail. This tells the memory system, give me, in this case, 10 integers, okay? And point this variable x, which is a pointer, to that, okay? So if x was like this, and it pointed there, and this would be out to 10, as it turns out. Let's see. 5, 6, 7, 8, 9, 10. 5, 6, 7, 8, 9. What did I do wrong? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I did one wrong. There we go. Whoop. OK. So this is what we've created. And then we say x bracket 3 equals 12. That's 12 goes there. And then we say star x plus 2 equals 5. Well, look. X points here. Plus 1 plus 2. Right? We put 5 right there. Everybody get that? That's how the pointer math works. OK, it's just arithmetic. Not that hard. And then we say cout, which means print, obviously. And it's well, not obviously. If you haven't done C++, that means like print to the screen. Cout asterisk x plus 3. And then it actually takes this value and prints it out to the screen, 12. And then it prints out the x bracket 2, which is 5. And notice we used the opposite ways of referencing them. And it prints out the same thing, right? So that's how the array actually works. OK, it looks like this. Why did I put question marks in there? Yeah. Yeah, that data in there are, I guess in Comp 11 you call them dead squirrels, right? Like that. And for those who didn't take Comp 11, I'm not really sure what that means either. It means bogus stuff. But supposedly, it's one of the other professors used it a long time ago, and we all use it now. But basically means bogus data, right? If we tried to say x bracket 0 right now, what we get is completely undefined, unlike in Java and some other languages where it would be 0. In this case, it's completely undefined. And it could be 10, or it could be 80, or it could be 1,000,004, or whatever. It could be anything. OK? So you have to be really careful that you know that C++ says, I'm not initializing your memory for you. OK, you just have to know that. OK, so we gave this a specific size. We gave it 10. All right, we gave it a size of 10. OK, and if we put all the other values in here, let's say we put I don't know, 6 and 4 and 99 and 1 and 0 and 13 and 7 and 12, right? We put all those numbers in there. And we wanted to put one more in there. We can't do it in this form, right? Can we say, hey, memory, give me another couple pieces here? Can we do that? No. Yeah, as it turns out, you're not allowed to. And let's step back a second and think about what the memory system has to do. When you say new int capacity, you're saying to the memory system, find me a chunk of memory that gives me enough space to put 10 integers. And the memory system says, OK, I'll do that. And here you go. Here's your chunk of memory. Don't go out of bounds, right? And in some languages, you're not allowed to go out of bounds. In C++, it's like the Wild West. You're like, oh, I'll go out of bounds all I want, right? And then you get these things called buffer overflows and hackers and all sorts of North Korea stuff and all that, But anyway, I hope they're not watching the YouTube. I don't think they get YouTube over there. Anybody from North Korea? OK. There could be, who knows? You never know. I don't want to tell jokes about a country or people sitting right here. Right? Maybe Canada. No, I'm just kidding. OK, so anyway, so the memory system says, here's your chunk of memory. That's all you get. And you can't go out of bounds. And I can't necessarily I can't give you extra tacked onto that. Right? It would be kind of nice if we could. Right? If we could say, I always thought it would be nice if you could say to the memory system, if possible, give me extra space at the end of my array. And then if you can, it returns a certain value and says, yeah, you were able to do it, or whatever. I think that would be kind of cool. But nobody ever took me up on that. So I guess we could hack the Linux kernel to do that maybe or something. But anyway, you have to say to the memory system, if you want to make it bigger, give me a new array that's bigger in some form or another. Now, normally, how much bigger do we make it? A lot. Good answer. I heard a lot of double, right? We generally double the size. Now, could we ask for just, if we're going to add one more, sometimes it might make sense to just say, hey, give me one more, right? But normally for arrays, we double the size. Any ideas why?
It takes a ton of time to copy the array to the place.
Because it takes a ton of time to copy the array. Not quite. I don't think that's necessarily the, well, maybe subtly that is. You had your hand up back here. No? Somebody back here maybe? Yes. What do you think? Yeah, go ahead. Yeah, go ahead.
Every time you double it, you have to double it like less.
That's, yeah, I like that answer where you're kind of going through the same thing where you're saying, look, it takes a long time, don't do it as often. But yeah, if you start out with 10, okay, and you want to get up to 1,000,000, you know how many times it takes to get to 1,000,000 from 10 doubling? You could figure it out if you wanted to, but is it like millions? No, right? It's not that many times. We can figure this out by just, you can kind of hand wave it, right? 2 to the 10th is basically what you're looking for, right? Or sorry, 2 to the 20th is about equal to 1,000,000, right? 2 to the 20th. So it takes 20 times to double to get up to 1,000,000. Now, if you're adding 1,000,000 things, doubling 20 times is not that many times, right? It just really isn't that many times. So you're absolutely right. You can get big fast is what you want to do. And what's nice about that is, let's say you're writing a program and somebody's going to be able to add an array, like put numbers in an array, and you don't know how many numbers, right? But you could be up to like 1 billion, right? Some people might think, oh, if it could be up to 1 billion, I better give them 1 billion spaces immediately, right? And that's not a good idea because that just wastes memory. What if 99 times out of 100 it uses 5 integers, and the 100th time it uses 1 billion, right? You don't want to make it 1 billion because 99 times you're going to waste way too much memory, right? So make it small, all right? And you'll find that the doubling part doesn't really take that much time to get big because of that. You're doing it less and less frequently. OK, so we ask for the doubling. And this is the expand part of the homework assignment, right? Let's follow some of these instructions and see exactly what's going on when we're going to expand this array. OK? So the first thing we need to do is we need to say to the memory system, give me more memory. In fact, we'll say give me twice the amount of memory. OK? So if these are integers, in yours it's going to be cards, I guess, right? But if these are integers, you could say the following. You could say int star x2, which is our new array, right, equals, and then how do we get memory from the system? New, right, equals new int, which is what we want, the integers. And then let's say this is the 10 is, I guess it was initial capacity. Let's just call it capacity in this case. Capacity, right, times 2. Right? And that says to the memory system, hey, give me another array that has bogus information, but just give it to me, that's now twice as long. And instead of 10, it has 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Right? And now it's got those in there. All right? And now you've got your 2 pieces of memory. OK? x2 is a pointer, and it happens to be pointing to the beginning of that one. These are all these dead squirrels right now. All right? So you double it, you create a new one, and then you just copy everything over. Copying is easy. It's a for loop. I won't bore you with the details of that. But basically, we're going to copy everything over. 6, 4, 5, 12, 99, 1, 0, 13, 7, and 12. And now we've got another array that's big enough. And we've got all our stuff in there. And we're almost good to go. Right? We're almost good to go. We don't want to start using x2 now, and then x3, and then x4, and then x5. We want to always use x, right? So we need to first delete this array from memory. Basically say, thanks for giving me all this memory. Now you can have it back. Right? How do we do that in C++? Delete what? In this case. Delete x. Does that work? Almost. That would work for a non-array. If it was just one variable, it would work. You have to do these weird bracket, like square brackets, and then you say x. And that deletes what's in the array. Now, a lot of people confuse this. When you say delete x, especially if you don't have the brackets and you're doing some other thing, when you say delete x, does it delete the variable x? No, it doesn't delete the variable x. It just deletes what x is pointing to. This says, hey, x, what are you pointing to? I'm going to go delete. I'm going to give back all the memory that you just got earlier. OK? Where is x pointing after I do this? Dead squirrels is still pointing right there. Yeah, nothing changes about it. It's still pointing there. And in fact, some people have like bugs that are really hard to find when they do this, forget that they've deleted it, don't change it, and then are all of a sudden still accessing memory. And then it might work for a little while. The memory system doesn't say wipe this. The memory system doesn't set your x to null. It doesn't do anything. It says you know what you're doing. So we'll just let you, have horrible memory bugs. Right? But anyway, now you've deleted this one. It's still pointing there. But now you just need to point it to here. Right? How do you point this one to where this one's pointing to? X equals x2. That says point x at what x2 is pointing at right now. And that changes this guy to point right there as well. The next thing people tend to do a lot of is they say, oh, I'm not using x2 anymore. I better delete it. Right? And then they go and they write delete x2. And first of all, they forget the brackets. And that just screws up. And it almost always crashes and whatever. Because you don't need to delete this variable. If you never use it again in your function, who cares? Right? It gets the variable itself kind of goes away when the function ends. But the memory stays being pointed at by x in this case. OK? So don't do this. Don't try to delete x2. OK? And then some people get an error there where it says x2 shouldn't be deleted like that. And then they go, OK, I'll just delete it like this, bracket x2. And then that actually goes and says, oh, all this memory you just gave me, I'm going to give it to you right back. Right? And then their program crashes later, and they don't know why. And TAs lose sleep helping you, all that. So don't do that either. OK? So the point is, once you set these together, this is what you're going to worry about. Don't worry about that anymore. Who cares if it's still pointing there? It will eventually go away. Yes?
How did you say again that you
I'm just going to use a for loop. I'm going to use a for loop. I know how big this one is. It happens to be the with current capacity if you want. Or it happens to be the number of elements or cards held or whatever. Right? Yes?
So why do we have to do the delete brackets x if we're just going to reassign what x is pointing at to x2? Because once you've done that, the initial array has nothing pointing to it. So can't they just like garbage collected? Or
So C++. Are you a Java programmer?
that's how I started.
Yeah.
Yeah.
C++ does not have garbage collection. You have to do it manually. And we'll get to this in a little bit when we talk a little bit more about memory management. But for managing memory, if you use new, at some point during your program, you have to use delete to give it back. Right? Now, is it the end of the world? When your program ends, the memory system says, I'll take all of it back, no matter what you want. Right? But we want to be good programmers. And if our programs are ever going to be used in a bigger system, we don't want them to. This is called a memory leak, if you forgot to do that. Right? If you didn't do this, and you all of a sudden pointed x to here, for the rest of your program, this would be available to you, but you would have no way of actually accessing it. Yeah. OK? So that's that. All right? Other questions on that? One last thing we have to do, we have to actually update the capacity, because the capacity for this one was now, let's say, 10. And for this one, it's 20. So you need to do capacity equals capacity times 2, or whatever. OK? Yes?
So if you make it do x equals x2 before you delete x, you just then can't access that block of memory at all.
Right. Right. You can't access this memory at all. Yeah. OK? Question came up earlier. So we're doing this delete right here. Do we need the delete in the destructor?
Yeah.
Why?
Because in this function, at least, you're making a new array even after you delete the old one.
Yeah. You're making a new array here, and then you're not deleting it until the class actually ends, and that's what the destructor takes care of. So the destructor basically says, I'm going to delete the last one that you created, because you're not going to do it until that point. But this delete says, I'm going to do the last one, and now I'm going to create a new one immediately, or it's already created immediately. Yeah, very good. Everybody get that one too? Talk more about memory management in a few minutes. Okay. All right. So we've expanded, and this is all the code that you need to do to expand. Right? This is all the same stuff. You'll see this in your homework. And you'll see this in a number of other array-based data structures that we use throughout the class. Queues is a good one. In fact, circular queues is a case where we do this, where we have an array, and you don't even know what queues are necessarily, but we have an array, and we need to double it. Now, we need to do a little bit more than just copying. It's a little bit, well, it's copying in a special way, which we'll talk about when we get there. But you'll see this pattern a number of times. OK? And by the way, if this class was taught in Python, you wouldn't even have to worry about this stuff, right? Because it would be garbage collected, and because there would be other like behind-the-scenes thing that we don't have to worry about. But now you know a little bit more about the memory system and how it works, for what it's worth. Question? No? OK. Anybody else? Questions on this? Expanding the array? By the way, I'll get lots of emails or Piazza posts that say, hey, my program's crashing in something you wrote, right? And I always chuckle a little bit because, A, I definitely make mistakes, and that happens, right? But some of these things, like if it's crashing in something that we provided you, definitely bring it up if you've done all sorts of, if you've looked at it very closely. But many times, if you forget to do this, or if you do this for the wrong variable like x2, the problem manifests itself much later. And those are hard bugs to find. Right? This is what people like programmers rip their hair out because they forget to do stuff like this and then can't debug it because it happens, it ends up crashing in the print function you didn't even write. And it's because you didn't do something, many functions ago. So it's tricky. Does make it a little hard to do some of this debugging. OK? All right. So what other list functions from the abstract data type do we have? Well, these arrays are pretty simple things, right? They're memory locations. We can access them. But we can say lots of stuff about them to fill out our list abstract data type or interface, right? We can say whether it's empty. We can make it empty, right? Making it empty is actually a number of people asked this, right, in class or on Piazza. A few people asked this. They said, if I delete something from this, what do I have to do? And the answer is what? I mean, if I'm, let me flesh this out a little bit, right? Let's say that for this array, for the top one, before we do all this other changes and things, let's actually make it so x still points here, and our memory system still has it. For this array right up here, OK, the capacity is 10, right? The number of integers, in the homework you'll call it cards held. Let's say it's the same. Cards held equals 10 in this case. OK? All right. If you want to delete one from this, the end one, let's say you want to remove from the end, right? What's the only thing we have to do? Yeah. Yeah, cards count minus minus, because you don't necessarily know that it's the same, right? But you would say cards held minus minus, which would make it equal to 9. And even though there are 10 things here, this one doesn't even matter to us anymore, because it's really a dead squirrel at this point. Because all we've said is from an abstract perspective, there's only 9 things in this array. It has a capacity for 10. There's only 9 things. If you added one again, it would go in that spot and overwrite the 12. But we don't care. Can anyone think of a time where a programmer might actually want to make that 0 or some other value? What do you think?
So that you know when you've gotten to the end.
So that you know when you've gotten to the end. Well, that's one way to do it. But if we keep cards held, for instance, updated properly, we don't ever need to use that. Some other situations. What were you thinking? Debugging? Yeah, that's not a bad idea. If you want to like check and see what you want to make sure that it's there. I'm thinking of one that's more globally like worrisome to people. Yeah. 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 So when you when you log on to a system, when you log onto the homework server, what do? What do you actually type? You type your username, and then you type your password. And if they stored the password in some memory location, then somebody sneaky came along and figured out where that memory location was, they could go in there and say, your password is 6451290, whatever, right? So there might be a case where if you're removing something, you actually want to go in and say, hey, erase, like overwrite it with some bogus data, right? So security implications would be a very good reason why you might want to do that, okay? If you were creating a real poker, like poker hand game, right, you definitely want to do this, right? There are times when there are online poker's been around for a while, right? And there were lots of people who tried to hack in and were successful at hacking into online poker. And we're talking about real money here. Like people like basically stole or hacked such that they cheated on the game by looking in the memory locations and seeing what other players had, right? And how do you do that? Well, you're not very good with security. So these days, it's very tied down. Like the online games people are much better at keeping this out. But smart hackers were able to make like lots of money that they siphoned right down to like the Caribbean or something. So, you know. Anyway, all right. So that was kind of takes care of the remove from it. If we remove from the head of the list, if we remove here, can we just say that cards held equals 9? No, you can't in this case, because that would say, oh, it only goes up to 9, right? If you remove this one, you do have to move all these ones back 1, right? And that's another for loop. And that actually takes time, right? This is a slow process. This is a fast, sorry, the other way around. This is a fast process. This is a very slow process. Why? Because if you've got 1 billion integers in here or 1 billion cards, right, and you're removing from tail, you've got to move 999,999 of them, right, which takes time. If you're moving from, sorry, if you're moving from head, I keep getting that backwards. If you're moving from the tail, you need to not even do any, not move any. So there's the difference there. Okay? We'll get into more details about those things later. OK. Behind the scenes, right? These are all array things. We've already gone through this. These are all array things. The isEmpty is another one-liner, by the way. IsEmpty says cards held equals 0. That's it. Boom, you're done. No need to write it over. No need to worry about that. Okay? All right, we all already discussed enough about all these other methods, I think. I think we're good to go there. Okay? All right, now, how do you test your code? Well, one way to test this function, let's say we want to test this function, insert at tail. Okay, we're going to insert at the tail over here. The way we're going to want to test this is we're going to want to say, here's a little mini program that does just enough work to show us that insert at tail works. And you might want to test it for a couple different cases, but you want to do that. Sometimes you can't just test insert at tail because you need to do some other setup and other things need to be happening. But you try to test those things first. Make sure those things are working, and then test the insert at tail. Let me show you a little piece of code that, that might work for that. New main function, and let's say it looks like this. Okay? Create a list dynamic array, which is what you guys are all writing here. And then we create a card. The card happens to be the ace of diamonds. In fact, before I even go through this, we have enough time. Look at this code. Talk to your neighbor. Tell me what it prints out. And I'll tell you when it prints a list, it prints the, let's just say that it prints like 3 of clubs, 2 of hearts, 5 of diamonds, like that. Talk to your neighbor. Figure out what it prints out. And then
Jack is 11. Sorry, I was wondering where you're getting J from. Sorry.
Okay, what's it print out? Yeah.
AD, and then the next line will be ADTH.
So it does AD and then ADTH like that. Does everybody get that? Okay, is this a hard test? No, it's a really simple test. But it will show you, at least for a couple cases, that insert at tail works pretty well. Right? You might want to do like more cards, right? Repeat for more cards down there, right? But in this case, it would, the first thing you do, you insert at tail AD, it puts it right at the beginning, and then you print it. That's great. And then you insert at tail again, which means it puts it after that one, and it should print that. So these kind of tests are the kinds of things you want to write. Question? No, OK. These are the kinds of little tests you want to write. And these are the kinds of things we will actually be running our provide tests on. Some of them are a little more advanced than this, but not really. I mean, really, we're just trying to say, hey, does your insert at tail function work? Right? Not hard. Not really that tricky. OK? I gave you some other examples on Piazza. Let's see. Here we go. This is actually straight from the provide script. Let me make it a little bit bigger. Right? Straight from the provide script. And what it does is exactly the same thing. It creates dynamic array, creates some cards. Look, it's even an ace of diamonds like before, right? Insert at index the card number and what index you're doing. It's 0 in this case. Print it. Change the suit, change the rank, print it. So you can look through these and see what's it supposed to be doing, and then why isn't yours doing that, right? And we will run all these tests on here. And you can just change your main to do this, right? And if you want, comment all this out. Be careful, because it turns out you can't use these /* comments nested, meaning you can't take another /* up here and then down here. I don't know why. It doesn't seem like it's that hard to do, but they didn't want to do it. Anyway, you'd have to do like / starting here. But anyway, comment all this out and then uncomment excuse me, the next one. And you'll be able to run this one. And this one, same exact thing. Look, it's even an ace of diamonds again, right? Same sort of thing. It just does a little bit more. Tests a couple other things. OK? And it actually tells you right at the top here. Should probably put that too. Test the card at method. OK? Writing tests is not hard. It just takes a little bit of diligence to do it, right? To make sure that it works. But if you write your own tests, that means they'll hopefully provide will pass your stuff. And by the way, don't use provide to do like your testing. I know I give you like 100 provides. You'd be surprised. There are people who provide like 38 times, right? Because they're, oh, that one failed. Oh, let's change this. That one failed. No, take it, copy it in, and you know. Another Unix tip. If you want to, let's see, if you want to put the output into a file, let's say you wanted to put the provide output into a file, you could type, let's see, homework 1, you could type make provide, and then this little greater than sign, and then some file name, and it will put all the provide output. The only problem is when you hit return, it also puts the prompt that says, please type yes or no. So you actually have to type yes, and then it's running your code now. So you can do that. But if you want, it will actually put all, we'll wait a second. And I forget if I have bugs in this one or not. But we'll wait a second and see what if it actually prints it all out. It should. And does this. And that's the way. And then you can actually use either less or more or cat to actually see the output of your program. Okay? Sometimes it flies by on the screen too fast. So there you go. OK, so let's see. Less some file.txt. And there we go. It says provide hello, me, receiving solution, da-da-da-da. Here's the solution. Copying all files. Testing main 1. Passed. Running Valgrind, which I'll talk about in a second. Passed. Et cetera, et cetera. Right? Oops, no, it didn't. I put a memory error in there. So it says leak summary. Definitely lost 88 bytes, right? So my program, that's right, I was going to show you this live. Well, there you go. Definitely lost 80 bytes. I'll show you that in a second on how to do that yourself. But it tells you exactly what you do, OK? Or how it works. OK? Quit. There we go. OK. So that's testing. All right. We already talked a little bit about memory management. OK, but in C++, there are a number of ways to define an array. Right? You might have seen it like this before, where it's just card hand bracket 10. This actually is an array of 10 items. This is created when your program starts, or at least when your function starts, whatever function it's in. And it is managed for you. When the function ends, you don't need to do anything about it. Right? You don't need to give it back. This one is the one we've been using before, which is dynamically given. And it's actually from a whole different place in memory, as it turns out. You don't need to know this. It's kind of extra information. When you do this, this is created on what we call the stack. And the stack is a place in memory that's for your program to run in. OK, your program gets a certain part of memory and says, this is yours. And when you say card hand 10, it says, oh, OK, I'll take that from the stack. Generally. Yeah, I think it's generally that way. This one says, no, I'm going to take it from this thing called a heap, which is kind of like a heap of memory. It's a little weird. I mean, it's a weird analogy, but it's like a heap of memory. And this is when it says, hey, memory system, find me a piece that I can use. OK? This one, you need to use delete on. This one, you do not. You need to use delete on. OK? Anytime you use the new keyword, that piece of memory must be deleted. OK? All right. Anytime you do it. So this is the tricky part, right? This is exactly what we were talking about earlier with sometimes you use delete in the middle of a program, like when you're expanding, and there might be one left over at the end that you have to take care of in the destructor. OK, that's the tricky part. When we talk about other data structures like trees, at the end of your data structure, you have to walk through the entire tree and delete, 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 delete. It's definitely a little more tricky, but we'll get there. OK? And by the way, destructors and constructors get called automatically. Don't try to call your destructors and constructors yourself. It will not work. Things will break. And it's a bad error messages that are hard to decipher too. Okay? There's this program that I mentioned earlier called valgrind. And what it does is it tests for memory leaks. Yes?
What did you mean by that statement that like the destructors and constructors are called automatically?
So you create the destructor and you create the constructor. Well, some constructors you can call by virtue of creating a new function or creating a new object. But you don't actually explicitly ever say the function name bracket, or you never say the little tilde function name or class name to call the destructor. It does it automatically. When the class gets destroyed, the destructor gets called by the compiler. It sets it up to do it all by itself. Yeah. Yeah. If you don't have a destructor, it creates one for you that's empty, and then calls it. But that's what it does. Yeah. OK. So there's this program called valgrind, which you can run in your programs to test for memory leaks. OK? And if we find memory leaks, we will take points off. So make sure that you write your destructors properly, and make sure you do all your deletes properly. OK? We need to test you on those because we want you to do proper memory management. It's kind of painful sometimes, but you'll get used to it. OK? Sample output. This is kind of like what I showed you before in that little test we just did. It'll tell you if you lost memory. OK? And it actually says run with leak check equals full to see the details. That will tell you where the memory got lost. I'll show you that in a second. So it's actually a good way to debug it if you're finding it. What you want it to say is this. All heap blocks were freed. No leaks are possible. OK? That's what it wants to what you want to see. In fact, we look for that line when we test it. If it says all heap blocks were freed, we said, great, you win. You pass. You pass. You win an A. Let me show you how to run that leak test itself. OK. So we did, let's do this, valgrind ./homework1, which is how we would run it. It runs the whole program, and it says, you definitely lost 824 bytes. Darn. Where do I lose them, valgrind? Well, rerun with leak check equals full. So we say, OK, valgrind -- leak dash check equals full dot slash hw1, and it will give me more information. And it gives me lots more information. And it says right here, it says, look, on line, let's see, of my functions, on line 220 of list dynamic array, we called the expand method. And inside that expand method, there's a new, and that new never got deleted. So guess what I forgot to do? I didn't write my destructor. So that new was created in the last time my program was or my array was expanded, and it said, oh, it never got freed. And so you can find it that way too. It's kind of nice. Okay, so pretty cool. You can actually use this stuff to help debugging. Yes.
Is it important, like, whatever blocks
Is it important which blocks they are?
like, I just don't understand that. It's like you said, like 88 blocks in, 88 bytes in one block.
Yeah, don't worry about the number of blocks. It's just more information. If you want to dig deeper, you can dig deeper, but it's not that important about how much it is. It's just the fact that it's not 0 is the important part for our class. Got it. OK. All right. So it's about all I've got. There's some advanced reading for you if you want to go and look up some stuff. There's also references as well. Whoops. The date is wrong, though, on there, so I'll have to change that. Any last-minute questions? OK, if you have add forms, I will happily sign them. If you have other questions, come on up. And I will see you guys either at the review or Monday.